Good afternoon. My name is Nicolas Rinaudo. I work for a Swedish company called Besedo, where we do a lot of online content moderation and machine learning. And I am here today to talk to you about optics. Because, well, the Scala community is a bit weird about optics. We don't talk about it much. If you take any other FP community, say Haskell, for example, they talk about lenses and optics all the time. If it's not lenses, it's servants these days, and they talk about it a lot. And with such awe and reverence that you'd think optics were a theory that was gifted onto us by a god of pure intellect and shining beauty, which is fair enough, really, because it's pretty much exactly how it happened. But in the case of Scala, we don't talk about it much. And I find that a bit surprising, because it's a very useful concept. And I think that one of the reasons we don't talk about it much is because optics and the vocabulary we use to talk about them are very intimidating. We have words like foci, lenses, prisms, profunctory optics, covariant helomorphisms, these kind of things. And I made one of these up, but the fact that some of you don't know which one I made up, that is exactly my point. The vocabulary is very confusing. So, at least personally, I was terrified by the whole thing for the longest time, and I didn't want to learn them. It sounded way too complicated. But one day, in a fit of madness, I sat down and decided to study optics. And I discovered that if you ignore the theory behind them, beautiful though it may be, and it is beautiful, but if you ignore that and you focus on what they're used for, they're actually very useful. They will serve practical day-to-day problems that you've had in your business life. And they're surprisingly easy to understand if you don't get bogged down in the theory. So my goal today is not to make you expert in optics. We have about 40 minutes, so that's not going to be enough. But I do want to add that to that database of tools that you have in the back of your head, so that one day, when you actually find yourself in your daily work faced with a situation where they might be useful, that your brain can go, hang on a second, you've seen a talk by this weird French guy about that. Maybe you can use that, and if that happens, then I've done my job, and this is exactly what I'm standing here in front of you. So if that happens, let me know through Twitter or whatever, and that will make my day, because this is what we're doing here. So, with that out of the way, the one prerequisite we have before we can start talking about optics are algebraic data types, which is something I'm going to be calling ADTs from now on, because algebraic data types is not a word a French person is equipped to say too often without pulling a muscle. So ADTs is going to be from now on. And, well, since it's so important to the talk, I will be giving you a quick rundown of what ADTs are. So, algebraic data types. And through the course of this talk, we're going to be working with a couple of types, which I'm going to introduce now. The first one is a classifier, in the sense of the machine learning classifier. And if you trim the machine learning classifier down to its minimum possible expression, it's going to be a name, which is how you identify the classifier, and a number of classes, which is how you make sense out of the probability distribution that you get back from the classifiers. And in terms of code, we're going to represent that as a classifier, which is a name and a class count. And if you pay attention to the way I phrase that sentence, it's very important. Classifier is a string and an int. It's an aggregation of types where the aggregating operator is AND. And that is what a product type is in a sense. This is all you need to know about product types, aggregation of types with an AND as the aggregation operator. And I'm going to be representing them through diagrams. Clearly, I'm not great at diagramming, but this should still prove useful, where the product type itself is going to be represented as a trapezium with a large base, because it kind of makes it look like the AND mathematical operator. And then you're going to have vertices bearing the name of the field that composes the product type, and then the actual type of the field as a generic random blue box. And this is how you represent the entire classifier, the entire product type. Now, we are going to be trying to query this classifier through, say, an HTTP API. And in order to do that, we're going to need some sort of authentication through a type that we're going to call auth, which within the context of this talk, we're going to limit to a token-based authentication and a login-based authentication. Token-based, you have a token provided to you by the server, stick that into an HTTP header, send that to the server, you're authenticated, everything works fine. And login is a username and a password, for example, for basic authentication. The code is a bit nasty. There's a lot of boilerplate. Scala 3 is going to make that a lot better. But what really interests us here is this. We have an abstract type called auth, which is either a token or a login. And that sentence should sound kind of familiar, because just before we had classifier, which was an int and a string. And this is a token or a login. And that is what a sum type is. It's an aggregation of types where the aggregating operator is or. And this is how we'll be representing it. So it looks very similar to the product type, but the trapezium has a slim base because this makes it look like an or mathematical operator. The vertices are dashed. I used that because I wanted to show that it's not quite realized yet. You don't know if the vertex is here because until you have a value of type auth, you don't know if it's a token or a login. So this is not a value that this is not something that you know ahead of time. And then the login, which is just a type in a random blue box. And now we have a classifier on the one hand and an authentication mechanism on the other hand. So we kind of want to put them together, which we will do through this type, ML service, which is an authentication and a classifier. So that's a product type, right? It's an AND. But it's not just a product type. It's a product type where one of the member is a product type and the other is a sum type. And that is usually what we mean when we say ADT. It's product types and sum types that you kind of jumble together, shake it, and get a nice data structure, which we're going to be representing as a diagram again, where nothing surprising here. You have this service, which is trapezium, product type, composed of a classifier and an auth. But we can go further than that because classifier is product type, right? So we can expand it. Auth is a sum type, and we know how to represent that. We did that before. And we can go deeper still because login is a product type as well. So let's expand that. And token is a product type as well. Not a very interesting one because it's only got one member, but it's still a product type. And this is a diagram that we'll be working with through the rest of the presentation. It looks intimidating, but hopefully we've taken it step by step, so you should be able to make sense of it. And we are going to be working at making it a lot simpler. That's the entire point of optics. And if you only remember one thing from everything I just said, this is what's important. A product type is an aggregation on type with an AND operator. Sum type, same thing with an OR operator. And when we talk about ADTs, we usually mean a graph of nested product and sum types. Do we have any questions so far? Because if not, I'm going to go straight into optics. But if you do have questions, it's a good time to ask them. Yes? Speak louder. OK, I'll give that a shot. Sorry. Yeah, I'll just speak louder. That's all right. If I forget, do let me know, and I'll try to raise the volume again. Just raise your hand, and I'll understand. So lenses. We're going to motivate lenses through this service, which got a lot of data put in, but the only one that truly interests us is the name of the classifier, which is news20 all lowercase. And the task that we have to realize is, for whatever reason, we want to turn that into an uppercase version of news20. So we want to set that to news20 where news is uppercase. Which, in terms of a diagram, means that we want to go from this massive thing to just that. We just want to go from the service, through the classifier, to the classifier name, modify that, and then get all the way back up and get the updated service. This, if we were to do that in an imperative language, such as Java, well, that would be very nice. It's a bit distasteful because it uses mutability, but it's very clear what's going on. You just follow the dots, and it's very understandable, very readable. Scala, not so much. This is a bit messy, and quite frankly, we only have 2 levels of indirection. I wanted to have 3 or 4, but couldn't make it fit on the slides, which is why we have such a small ADT. But it's a mess, and you know, FP programmers, we like to think we have all laws and proofs and abstractions which allow us to get rid of all of the boilerplate. Somebody else has done the work. We know these things, so we can just not write them. And we're supposed to write code that is elegant and terse. And clearly here, the work's not been done yet, because Java is much more readable than Scala, which is a problem. I'm personally not very happy with that state of being. So what we're going to do now is we're going to do the work so that we can express that in a way that is much more pleasant. So in order to do that, we are going to create a generic setter trait, which will allow us to set the values that we want to. So this setter trait has got two type parameters, S for state, which in our case is going to be the machine learning service that we want to work with, and then A for anything, I suppose. That's just a type that they use in the literature. And in our case, it's going to be a string, the classifier name. So our setter is going to work in a classifier to set the in a service to set the classifier name. And it's only got one method, set, which takes an A, so it takes a new value for the classifier name, takes an S, our service, and returns the updated S. So this is fine, but it is a bit disappointing because what we're trying to do, we're not trying to set the classifier's name to a hard-coded value. We're trying to modify it. We said we wanted to uppercase it, not to set it to a hard-coded value. So we would prefer to have a modify method that takes a function and does that for us. So we're going to add it. We now have this modify method, which instead of taking an A, takes a function from A to A. So it takes a function from classifier name to classifier name, and the service, and then applies a function inside and returns the updated service. So this is an improvement. But we could probably still make it a bit better, because if we had a way of getting the A outside of the S, we could write modify in such a, we could write a generic modify and not ever have to implement it again. So let's do that. Let's write a get method. And if we have the get method, which takes an S, a service, and returns a classifier name, then modify writes itself. We don't have to worry about it anymore. I'm not going to go through the code of modify. It's not terribly interesting. These slides are actually compiled, so the code works. If it's on the slide, it works. So don't try to find holes. It actually works. And well, there's something that bothers me a lot about this slide. We have a setter, and it's got a get method. And I've done 15 years of Java. I can't stand that. I can't call that get. So we have to find a new name for that for our setter, because it can't have a get method. We have functional programmers, right? So if we want to find a cool name for something, it's got to be slightly condescending. It's got to sound scientifical, and it has to make no sense unless you know why it's called that way. So we're going to have to come up with something like that. And in our case, what we're trying to do, because there's a sense, logic to all that madness, we are focusing on a part of a product type. We have a product type which is many types together, and we just want to focus on one. So we're going to call that a lens. It checks all the checkboxes, right? It's terribly condescending. It's sciencey because it's optics. And unless you know why it's called a lens, you have no idea why it's called a lens. So it's brilliant. I absolutely hate that name. But it's there. We have to work with that. This is what we've got. So this is what we have. The only difference between that slide and the previous slide is the condescending name on top, lens. And now that we have a lens, now that we have a lens type, well, we're going to be creating a bunch of them now. So let's write ourselves some creation helpers so that, well, essentially, so that my slides are readable later. So we do it the way we usually do these things. Take the companion object, stick an apply method in there, which returns a lens with the right type parameters. Take a setter function and stick that into the set method. Take a getter function, stick that into the get method, and you have a lens. But I'm going to go slightly further here, because I want to name a few of these types, because giving them names first is going to let you know that these are important and that we're going to be using them later. And I really want you to make a connection later. So this should be helpful. We are going to call the setter, so the function that takes an A and an S, classifier name and a service, and returns the updated service, we're going to call that a set. And the reverse is a getter, we're just going to call that a get. So the setter and the getter. Okay? So we update this slide now with these new names. This is the only difference in this slide. The setter is now of type set and the getter of type get. And now that we have all the machinery that we need in order to do what we wanted to do, let's quickly remember what we wanted to do. We wanted to do that. And this looks a lot, this diagram seems to hint like we should be doing that in 2 steps, right? First go through the service to the classifier, then from the classifier to the name. So let's create these lenses. And the first lens, service to classifier, is pretty straightforward. You have a lens which goes from service to classifier, which is a setter, basically a proxy for the compy constructor, and a getter, basically a proxy for just accessing the accessor on the case class. So that's our lens, which goes from service to classifier. Then we want to go from classifier to classify a name. Basically the same code. It is in fact so similar that you might be forgiven for thinking, well, this should probably be automatically generated. And of course it is. We're going to show later how to generate these things automatically so that you don't have to. And now we have both of our lenses, and we just can use them, stick them together, and write this. And that is extremely disappointing, because this is not much more clear than we had to begin with. I mean, I wrote that, I can't read it. This is very disappointing. And if we were to stop here, if that was the end of the talk, you'd be right for thinking, well, lenses are not that great. But I'm not satisfied, so I'm going to make that slightly better. And in order to do that, what I usually do when I find something messy like that, I stick it into a method, and into a function, and then parameterize everything I can and see whether a pattern emerges. So let's do that. We're going to create this setName method, which has a name parameter and a service parameter, and the body of the method is exactly the code that we had on the previous slide. I've not changed anything, just put things into parameters. Can go a bit further. I could also put the lenses as parameters. So let's do that. We now have the service classifier and the name classifier as parameters. And if you pay attention to this code, to the types, at no point do we use the fact that the first lens goes from ML service to classifier, and the second from classifier to string. The only thing that we're actually interested in that is that the two lenses commute, so that the first one finishes on a classifier, and the second one starts on a classifier. So if this is all that we're interested in, then let's make that in type parameters. Yes, that's the bit I should have done before, they commute. So let's make that into type parameters. And type commute, that's the only constraint that we have. And now the code is starting to look a lot cleaner. And if you focus on that bit, that should look familiar, hopefully. Because maybe 5 minutes ago I told you, I'm going to name these types so that later you can make a connection. Well, that's a connection I want you to make. That is a set from B to S. So given a lens from S to A and a lens from A to B, you can create the first half of a lens from S to B. That is interesting. Maybe we can create the second half as well, the get part. And sorry, just rename that to set so that it was obvious. And maybe we can create the get part now, which of course we can. It returns the get of S to B, and it's just you use the first lens to get the A out of the S, the second lens to get the B out of the A, and you have your getter. So we can compose lenses. This is brilliant. Given the length of S to A and the length of A to B, we have a length of S to B. Now that we can compose that, we can do this whole thing in just one lens, in just one hop, by composing our two previous lenses. So if we compose the lens from service to classifier and the lens from classifier to classifier name, then we get a lens from service to classifier name, which we can use as expected. And if you check it out, if you said I apply 2 uppercase to my service, I will get news20 uppercase, which is exactly what we set out to do, and it's a lot clearer and easier to understand than what we started with. So we've achieved the first part of what I really wanted to show you, lenses, what they're used for. If you only remember one thing about lenses, it's lenses allow you to reach arbitrarily deep inside of nested product types. That's the one thing that matters. Now, I'm going to move on to other type of optics. So if you have questions about lenses, now is a good time to ask them. Or if you need me to raise my voice. No? All right, cool. Okay, so in that case, prisms and optionals, 2 other absolutely brilliant names. To motivate them, we're going to take the same example, the same service, but this time, instead of modifying the classifier name, so instead of reaching for a product type, we're going to modify the username in the login value. So in terms of diagram, it means we want to go from that to that. And right away, we see there's going to be a problem, because that arrow in the middle, the dashed one, we haven't dealt with that before. So that's likely to pose something of a problem, but let's try to see how far we get without it. So first, we want to do that lens, service to auth. It's a lens. We've done that 3 or 4 times already, so no need to get into the details. But now we have to deal with that. How could we do that? Well, there's 2 ways we could go about it. First, there's a good one. And then there's the one we all thought of, which we all want to try. We know it's not going to take us all the way to the end, but we kind of want to ignore the problem and just pretend it's not here and implement it with a lens. It's not going to work, but when we do these kind of things, we know it's going to fail. We don't do them to succeed. We do them in order to see where it breaks so we can learn a bit more about our system. So let's do that. Let's see where that takes us. So we're going to want to create a lens from auth to username. And so auth to string, string being the username. And the problem is going to be in a getter method, because it goes from auth to string, right? And what we're going to do is we're going to pattern match on the service that we have, on the auth that we have, sorry. If it's a login, then it's easy. We have a user, return that, done. In the case of a token, though, we don't have a user to return, do we? And if anybody thought, well, we don't have a user, but user is a string. We have a token is a string, so I could sort of get that to type check, go in the corner. We're not going to do that, and I hope you understand why. I hope I don't have to explain why. So this is not going to work out. We're not going to be able to represent that through a lens, at least not in the same way. So, well, clearly we're going to need something different. We're going to need another data structure to do that. Remember the list of stuff that we have to do, some things that's arrogant and condescending, sciencey, all these things. And this, if you think about it in a certain weird way, is you take a sum type and you diffract it into its constituent parts. This is how you get a prism. So a prism, it's very similar to our lenses. It's also got a state type parameter, which in our case is going to be auth, and an A, which is going to be the login. And it's got a get method, which is different from the one from lens, because this one, well, it takes an S, just like the lens, but rather than returning an A, it returns an option of A, because potentially you don't have an A to return. In our case, if we have an auth, it might be a token, and if it's token, we don't have a username to return, so we return none. We also have a set, which looks a bit dodgy, because for the lens, we had an S and an A. We took the A, kind of tried to put it into the S, and then got an updated S. But in the case of Prism, we're not setting a field, right? We're replacing the auth by a login. We have a login, and we want to say, well, that's going to be an auth. So we kind of squish it instead of the auth. So this is why this set only takes an A, which is a login, and returns it as an auth. And then we have modify, which is utterly boring and we're not going to bother with. Same as before, we're going to write a couple of creation helpers. Nothing fancy here, exactly the same code as before, except for this one bit here. This is not going to be pleasant to write, is it? How are you going to implement that? You get a login, you get an auth, and you're going to pattern match on that. If it's a login, return the user wrapped in a sum, otherwise return a none. It's going to be a lot of code to write and always the same code. So let's simplify that a bit by using Scala weirdnesses. Scala has a few quirks. Does anybody not know what a partial function is? Do you guys need me to explain what a partial function is? Yes, a couple of nods. Okay, so a total function is a function that is defined for the entirety of its domain. So typically the square root from positive int to floats is total, because there is no positive int for which the square root is not defined. On the other hand, if you take the square root as defined from ints to floats, it's not defined for negative numbers, because you can't get the square root of a negative number and get a float. So that's a partial function. It's defined for some elements of its domain, but not all of them. And in Scala, we have a type that represents partial functions, which has two interesting properties. The first one is that you have a lift combinator, which allows you to go from a partial function of A to B to a total function of S to option of B. That sounds a lot like what we want. So we could use that. And another interesting bit about partial functions is that in clear violation of the Liskov substitution principle, there are subtypes of functions, which is completely idiotic, but allows us to have some fairly nice syntax, because when you have a function that takes a function as a parameter, you can stick a partial function in there, and it turns out pattern matches are partial functions, so it's going to work out. We are going to write this function from partial, which, taking a partial function instead of a total function, lifts it and sticks it into the other constructor. This is going to allow us to write this link as a prism from auth to login. The setter is not terribly interesting. It just takes an A, which is a login, and upcasts it to an auth. And it type checks, because one being a subtype of the other, just the compiler is happy. And the second one is a pattern match, but it's just a pattern match on the bits that interest us. We can ignore all the other cases. We don't care about them because that makes it a partial function. And Scala is going to turn it into a S to option of A. So that's going to work out. So now we have two of our links. We have the links from service to auth. We have the link from auth to login. How are we going to compose them? Because we know how to compose lenses, right? But we haven't yet composed lenses and prisms. We don't know how that works. So what could it be? Could it be a prism? Could we use a prism to represent the outcome? Well, we can't really. There's a problem with a setter. Because a setter is a function of B to S. And there's no way to get an S out of this method. Because through the prism, we can go from the B to the A, and that's fine. But there's no way to go from the A to the S. So we get stuck. If you don't believe me, the slides are available. Just put the whole thing into REPL, try it out. It's not going to work out. And if it does, I really want to hear about it because that's going to put this whole thing under a train. I'd love to hear about it so that I don't have to do this mistake again. But basically, you can't. So it's not going to be a prism. Could it be a lens? Well, we're going to have a problem again, but this time with a getter method, where we want to go from S, and we get an S, to B, but we can't get a B. We can get an option of B through the prism, but we don't get a B. And I suppose that the person who before thought that by using a token he would type check and be all right is thinking, well, yeah, but option does have a get combinator. For the same reason, we're not going to do that. So there's no sane way of doing that. It's not going to work out. It's not going to be a lens. So clearly, we need something else. Another data structure, same checklist as before, and then we get very disappointingly optional. This is kind of where the whole thing broke down. It's not an optic, it's a boring name. So apparently, I got Julien Truffaut, the author of Monocle, told me this is not always called an optional. Apparently, it's sometimes called a fine traversal. We're going to call it an optional because a fine traversal is just really scary. So we have this optional, which takes an S, a service, an A, the login, and it allows us to go from the service to the login. The set method is basically the set method of the lens. It takes an A, an S, and returns the updated S. And the get method is exactly that of a prism. So an optional really is a mix of lens and prism. So the get function goes from S to option of A. Creation helper, nothing interesting to say here. We're not going to do anything fancy. It's just now we can create optionals. And right, now we have three data structures. We have lenses, we have prisms, and we have optionals. And we know how to mix lens and lens. That gives us a lens. We know how to mix lens and prism. That gives us an optional. Now we're going to go through all other combinations. So that's a lot of slides. I wrote all the code for you. We're not going to go through it because it's going to be really boring. But I'm going to go through it quickly, and I want you to pay attention because there's a pattern that should emerge. That is an important pattern to realize. So if you mix prism and a prism, you get a prism. Prism and a lens, you get an optional. Lens and a prism, optional. Optional and optional, optional. Optional and prism, optional. Prism and optional, optional. Optional and lens, optional. Lens and optional, optional. And we're done. You can start paying attention again. But it went quickly, so you might not have noticed. But there's a pattern. If you compose two lenses, you get a lens. If you compose two prisms, you get a prism. If you compose anything else with anything else, you get an optional. So usually when you work with optics, you kind of start with the clean ones, the lenses and the prism, but you usually end up with an optional somehow. And now we have everything we need, right? We have these two links. We know how to go from service to auth, and then from auth to login. And we know how to compose this. So let's compose them. And now we would like to have the last link, which is something we've done a bunch of times now. It's a lens. And we know how to compose the whole thing together because we've written all these composition functions. And we get an optional that goes from a service all the way down to the username if the username is here. And we can use it to set the username, which used to be jsmith and it's not psmith. And that works out. This is what we wanted to see. So that was what I wanted to tell you about prisms and optionals. And the main things to remember is that prisms are to some types what lenses are to product types, right? Product types allow you to go through, lenses allow you to go through product types. Prisms allow you to go through some types. And when you compose them, you get optionals. And then you can compose everything together. And that allows you to traverse complex ADT graphs. That is essentially all the optics I want to talk to you about today. So if you have questions, we can go through them. We have another 15 minutes roughly. Or I can show you some libraries that implement optics. No questions? Yeah, there's a question in the back.
Lenses and prisms, because I want to 5 data structures with some fields and need to write a lot of prism and lens just to read the data.
So I didn't pay him to ask that question, but that's what I'm going to answer next with the libraries. So if you wait just a few slides, you're going to have the answer to your question. But yeah, of course you can. Of course you can. That's the point.
Any other questions so far?
Nope. Okay. Good. All right. So I'm going to talk about the ecosystem now a bit. I'm not going to mention all optics library because there's about as many of them as we have JSON parsers. That's too much to fit here. But I'm going to talk about 3 main ones. And if you maintain one and it's not mentioned here, it's not because I didn't like it. I probably don't even know it exists yet. So apologies for that. The first one, of course, is going to be Scala Z, isn't it? Scala Z is always somewhere around the corner being weird. And it's being really weird here because it only has lenses, it doesn't have prisms, it doesn't have optionals, so it's not even as good as what we've done so far. And for whatever reason, lenses are called lensu. I don't actually know why. It's just weird. And the syntax is exactly what we had before, isn't it? So it does what we did before, calls it lensu just to be different, and doesn't even do the prisms and optionals. So it's a bit crap. So if you already have Scala Z in your class path, all you need are lenses. You don't mind the boilerplate. Use that. Otherwise, use one of the alternatives. The use site API is basically the same as ours. It's not curried, but that's a minor detail. But yeah, that's Scala Z. It's there, I suppose. And then, of course, if you have Scala Z, you must have shapeless. And shapeless is actually pretty brilliant. I don't know about you, but this code is absolutely beautiful, isn't it? You just say, well, I have a service, I want a lens on that. Then you work it out. I want the classifier, I want the name. Not my problem, you work it out. And it does. Shapeless will work it out eventually. Sorry. It will work it out, and it's proper amazing. And if you look at the code for that, it's actually understandable, and it's really, really, really nice. The problem with shapeless, of course, is that being shapeless, and the way it works, when it doesn't work, when you haven't lined everything just right, instead of telling you, well, you've missed that bit, it's going to tell you, I need an implicit. I don't know which one. I don't know where it could come from. You work it out, not my problem. So it's great when it works. And if you already have shapeless in your class path, then by all means use that. But do know that you will waste a couple of afternoons working out where the hell that implicit should be. It's also being a bit weird because it's got lenses, that's fine. It's got prisms, but not optionals. But just for fun, they decided that what they call prisms is optionals. So they have optionals, but not prisms. Or is it the other way around? It's confusing. I don't know. It's just you have everything you need. It's kind of hidden anyway through this beautiful syntax. So you just write that, it works out, you hope, and when it does work out, you're done. And it's honestly, I make fun of it, but it's absolutely gorgeous. This is absolutely beautiful. The use site API is basically the same as ours. They just inverted the parameter names, but who cares? And also, prisms optionals, weird, but it works. And finally, the one library that I recommend you use, if you can, is Monocle. Granted, it could stand to be a bit more terse, because this all composes, but the composition operators are not very nice, and you have to type everything explicitly all the way down, so it's a lot more wordy than shapeless, clearly. But on the other hand, it's also a lot more powerful because it implements a lot of optics that shapeless doesn't have. So I'm not going to talk about them much because they're really complicated and I don't want to lose you. But I'm going to lose myself anyway. I don't understand these other optics. But just to give you a quick teaser, what we've done so far, we have optics that allow you to work through one-to-one relationships. So lenses allow you to go from one node to one node, and you know that link is going to be here. And lenses, no, prisms and optionals are 1 to 0 or 1 relationships, right? But you could go from one to many relationships, such as with list, for example. List is an ADT that is recursive. It's defined in terms of itself. So it's got an infinite length, and you have optics to work with that. Not going to talk about them because they're really complicated. And I don't really have the time for that, but Monocle supports them and a lot more. So if you need an optics library, Monocle is probably the one to go for. And I also know Julien, the author, has been putting out a lot of samples of how he's improving that bit here, that message, the username here, which is very unpleasant to read. And he's turned it into an API that looks a lot like Shapeless. So very soon there's not going to be any reason not to use Monocle, I think. And the use site API is exactly the same as ours, which is, of course, not at all a coincidence. And that is essentially what I wanted to tell you about the ecosystem. The important point to realize is optics are an important enough tool that free massive libraries that you must have heard about support them. I mean, you must have heard about them. Scala Z because of all the drama, and the other two because they're actually useful. And given these free libraries, these massive libraries support them, you have lots of choices. Use Monocle if you can, but you have lots of choices to have optics in your projects. Now, I have this. That's never going to fit in 10 minutes. So I'm going to skip that bit, which is a bit of a filler. And I'm just going to go through the last slide, which, scarily enough, is slide 257. That's a lot. If you only remember one thing about this entire talk, one slide, the one slide that you have to remember is this one. Lenses are used to go through nested product types. Prisms are used to go through sum types. You can compose them and you get optionals, and you don't need to understand the theory behind optics to enjoy the benefits. But the theory is absolutely beautiful. And if you're into these kind of things, do yourself a favor and study them because they're really, really beautiful. There's a talk by Simon Peyton-Jones on lenses, which I wish I could link, but it was a Scala Exchange talk, so it's gone. I think you can find it. I found it on a dodgy Japanese website called Blibli or something like that, where, yeah, it's a bit weird, in which Simon explains lenses and the profunctor optics theory. And Simon is an amazing, much better than I could ever be. His talk is much better than mine, but it is in Haskell, so it's a bit. But if you can hunt it down and look at that, it's much better than what I just said. And do we have any questions?